All right, we're looking at first principles in this video. Basically what this means is getting the slope of a function, but the function is not a straight line. So if we look at the function, so for example, y equals x squared is this one, we can look at any in particular point. So if we look at maybe x is 1, we can sort of estimate the slope here. So if we pick 2 points really close, it sort of looks like the run roughly equals 1, and the rise roughly equals 2. So we might guess that the slope roughly equals 2 at this point. This is just sort of eyeballing, having a very rough guess. If we fill out the table, we can see that if x is 1, the slope is 2. If x is 2, we can sort of zoom in here, and it looks like it maybe goes up 4 and across 1. So the slope would be 4. And then we would expect the slope to be, well, there's a pattern to it. It goes 6 and then 0, minus 2, minus 4, minus 6. This is specifically for the function y equals x squared. So we have a formula for slope. dy dx is what we call it. And we can sort of see the pattern is 2 times whatever the x value is. So for example, 2 times 1, we do 2 times 2, or 2 times 3 to get the slope. Seems to be how it works. And we can prove this formally using something called first principles. So f of x equals x squared is our function. And we can say that f dash of x equals. Now some notation here. The slope we call dy dx. We also call f dash of x. So these are two names for basically the same thing. This is like if we start with y, but if we start with a function, we just call f of x. That depends. And we also call this the derivative of the function. Okay, so there's a formula for it. Limit as h goes to 0, f of x plus h minus f of x all over h. What a wonderful formula. So where this basically comes from is if we look at any 2 points and we'd like to find the slope, you can think about exactly what we're doing. So if we look at the point on our function, maybe like here, so at x, and then we look at another point here, let's say x plus h, and this is a function f of x. So this point here would have coordinates x and f of x. So f of x gives you the y coordinate. And this point here would have coordinates x plus h and f of x plus h. Now, really importantly, h is just the width between those two. Okay. So how do we find the slope between these 2 points? We go y2 take y1 over x2 take x1. So that's f of x plus h minus f of x. And it's x plus h minus x. Now the x's on the bottom are going to cancel. So f of x plus h minus f of x all over h is how that simplifies down to the slope. Now what we'd actually be calculating there is not the slope of the curvy line. We'd be calculating the slope of the straight line in between them. And as the 2 points get really close to each other, that more closely approximates the slope here at this point. So basically the derivative is going to be the limit as h goes to 0 of that expression we just found, x plus h minus f of x all over h. Okay, so this basically means this bit here, get the points close. Okay, now you can't actually just set h equal to 0, because if we set h equal to 0, this expression would just become 0 over 0, and we couldn't actually do it. The points would be sitting straight on top of each other. But with some algebra trickery, we can get this to work. So limit as h goes to 0. So f of x is x squared. I often like to write f of x plus h. You're just going to replace the x in this expression with x plus h. So that first bit is going to be x plus h squared. F of x is x squared. And we're going to divide by h. We're going to use this identity to expand out the top. So a plus b squared is a squared plus 2ab plus b squared. Or, you can FOIL it out if you want. Limit as h goes to 0. So x squared plus 2xh plus h squared. And then we still got the minus x squared on the end of that expression. Some stuff will cancel off. Now with first principles, anything without a h in it should cancel off on the top. And the x squareds, they don't have h's in there, so they're going to cancel off. 2xh plus h squared over h. And this is limit as h goes to 0, h of 2x plus h. And then we can sort of cancel off the h's on the top and bottom. So we had h out as a common factor there. That was the step there. So this is the limit as h goes to 0 of 2x plus h. And now that we're not dividing by h anymore, I can just set h equal to 0. So we get 2x, and I usually just say h equals 0 there. And that is our derivative. And before, we decided that if we had this function, the derivative would be 2x. So that's the y dx notation there, but f dash of x means the same thing. And that's how you find derivatives in general. We will get quicker rules for this, but for now we're going to use the full process of first principles.